Yeah, so I wanted to talk a bit about our journey over the past 18 months to build a Postgres data warehouse by integrating DuckDB into Postgres as part of the query engine. So yeah, as I said, I've been working on Postgres extensions for about 11 years now. First on at Citus Data, where we built distributed sharded Postgres extension, and later at Microsoft, and in the process also developed various other extensions like pgcron. I helped create one called pgDocumentDB, which implements Mongo in Postgres, and various others. But since last year, me and a few of my teammates went to Crunchy Data to start working with DuckDB and integrating it into Postgres. So most of the past 11 years was spent on this project called Citus. And it's basically an extension that adds transparent sharding into Postgres, so you can connect to any node and it'll route the query to the right node based on filters in the query, or it'll parallelize across all the nodes. And so when we started this project, we were definitely thinking about going into the analytics space, because at the time, you had Hadoop, which was pretty slow. Spark SQL was very early stage, always ran out of memory. Impala couldn't do many queries. So that's kind of where Citus started. But pretty quickly, we realized it was more natural for us to go into areas where Postgres was already a good fit for companies, such as software as a service applications that were growing rapidly and needed to scale their database. We also did quite a bit of real-time analytics, so you insert lots of data into the database and you build these sort of incremental aggregations in the database by doing sort of insert select commands in parallel. So it was pretty good for that, but it wasn't really a good fit for ad hoc analytics, business intelligence, or what's sometimes referred to as OLAP. Because fundamentally, Postgres is an OLTP database, and there's kind of these two factions in the database industry. These are like the OLTP faction and the OLAP faction. And these are different systems, different people. They don't really like to talk to each other very much. They do agree on a few things, like SQL is a good idea, transactions are a good idea. But when you zoom into the details, these are very different systems. And that's because OLTP systems, they optimize for a very high rate of queries that do relatively little work. Look up a row, look up 10 rows, update one row, and optimize for very, 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 very low response time, like millisecond response time. And then analytics databases, they don't necessarily do a lot of queries concurrently or at a high rate. But individual queries, they can scan through large amounts of data very quickly, and particularly targeting business intelligence, dashboards, reporting transformations. And so if you zoom into the details of these databases, they're different at almost every level, like the way functions are implemented, the executor, the planner, the storage. But one commonly recognized difference is that OLTP databases tend to use some form of row-oriented storage, where on disk you have row 1, row 2, row 3, and then there's an index that points you to the right row based on a particular filter. And that's usually really quick. In a few steps, you can find the row that you're looking for. So you can do a lot of queries per second, a lot of these queries concurrently. And a lot of the challenge of an OLTP database is to then also allow a lot of concurrent updates and inserts without slowing down. And an analytics database typically uses column-oriented storage. So a bunch of values from the same column are stored together as a block on disk. So this is helpful with fast projections. So if I only use 1 or 2 columns out of a very wide table with hundreds of columns, I only really need to read those 2 columns. It also lets me scan through the data a little bit quicker, but we'll get back to that. Now, the storage formats themselves are not really what makes the huge difference in performance in one area or another. Clearly, if you use column-oriented storage, looking up a row just becomes more expensive because you have to sort of reassemble it from different places. similar with updates. But what really makes the difference is the execution models that these storage formats kind of enable. Like in an OLTP database, the query execution itself, like the execution of the expressions in the query and the filters, isn't usually the big bottleneck. It's more kind of these walking through the index and there's locking. There's the query planning itself is actually often a bottleneck and more expensive than evaluating some expressions on a single row. But so what happens in a row-based execution model is we take the first row, we run the first expression, call a bunch of functions, go up and down the stack. Take this second expression, call a bunch of functions, go up and down the stack. Third expression, and then we take the second row and we go to the first expression again. And so this switching between expressions, there's just a lot of CPU instructions associated with that. And there's functions being called that themselves are usually not extremely efficient, do a bunch of allocations. It sort of wipes out your CPU cache a little bit. So there's a lot of inefficiency in this if you go through a billion rows. But for typical OLTP workloads, it doesn't matter. But for if you're trying to do analytics on this type of a database, you'd see that it goes very, very slowly. So with columnar storage, what we can do is vectorized execution. So we can take a chunk of values and then the expressions or the functions are essentially implemented as loops on a vector. And so that helps us avoid all this sort of function calling overhead. It helps with the branch prediction. It also helps keep our CPU cache hot. We just have the data sitting in CPU cache. And then it also, your CPU has these SIMD instructions where it can take a bunch of values and process them in one instruction. A lot of the challenge is then to kind of do this in parallel in a way that doesn't run out of memory, and it's quite hard to build this kind of vectorized query engine and have it be fast and reliable. So if you zoom into the details more, you'll actually find that everything is a little bit different. For example, OLTP databases have a very simple planner usually because they cannot afford to spend a lot of CPU cycles query planning, whereas OLAP databases, they evaluate a lot more different plans. And basically every detail is different. But now there's also these two databases that are more similar to each other than two OLTP and OLAP databases have ever been, namely Postgres and DuckDB. They both target single node deployments. They both are liberally licensed. They have very similar SQL syntax because the DuckDB parser is originally derived from the Postgres parser, and it also really tries to maintain a sort of Postgres query compatibility, similar functions with similar behavior. And they are both extensible. And that last point is quite important and quite nice. So especially with Postgres, anything that Postgres is not good at, we can make it good at by writing an extension. A few years ago, Postgres was not a good vector database. Now it's actually a really widely used vector database because there's pgvector and other extensions. You can make it a good geospatial database with PostGIS, a good time series database, a distributed database. So can we make it an analytics database? Like so far, the problem of doing that, it's really hard to build a good analytics database. But then DuckDB lends itself to being embedded into other software. Could be BI dashboards, Python scripts, but could also be Postgres. And from our days in Citus, we kind of knew that maybe like 1 in 4 companies we talked to when we were at Citus they were actually looking for a Postgres data warehouse. But it was just sort of too hard for us to build. But luckily now, there is a query engine that anyone can use. So the way this extensibility works is that Postgres is written in C, and extensions are usually written in C or Rust, and they get loaded into Postgres. And I mean, the simpler extensions, they just create functions and types, but there's also these more kind of deeper extensions that kind of go and mess with Postgres a little bit. So an extension can call any function that Postgres defines. It can also change global variables. And Postgres deliberately has some global variables that allow you to change different parts of its functionality. For example, there's a utility hook, which is actually just a function pointer that an extension can set. And then every DDL command and every other utility command will go through the extension. And the extension can just then decide what to do with that. It can decide to do nothing, or it can decide to send emails. I mean, but what it should probably do is call back into the regular Postgres DDL logic. But maybe for some commands, it can do something special. Similarly, there's all these query planner hooks at different stages of query planning. So it can propose alternative plans to Postgres. It can also say, Postgres, what you wanted to do, don't do that. We're going to do this. And so that gives you a lot of flexibility to kind of carve out a piece of a query plan and do things a little bit differently than Postgres normally does. Similar for query execution and similar for also writes to tables. And what we can then do in an extension is create a new type of table, for example. Postgres has heap tables. That's the sort of default storage format. But we could add an analytics optimized table format. And then a lot of the operations, when you query that table or when you do schema changes on that table, we can do some other behavior and maybe take advantage of DuckDB. Though we need to decide how would we store such a table. So we could store it in a DuckDB file that lives alongside Postgres. That can make a lot of sense because the DuckDB native format is generally the fastest or faster than using Parquet for some scenarios. The problem is Postgres is often used in a replication topology where there's this physical replication from a primary into a secondary, and only the things that go into the Postgres write-ahead log or the Postgres buffer manager are going to get replicated. So if there's just another file sitting on the disk, that's not going to make its way into the secondary, so we lose that data if we ever switch to a replica. And this is important if you have a sort of high availability setup, but it also is a common way of just doing upgrades in Postgres, that you just spin up a new instance, replicate from the primary, and then switch over because you have very little downtime for the upgrade then. So another thing we could do is, okay, well, the write-ahead log gets replicated. Could we put the data into the Postgres buffer manager and the Postgres write-ahead log so that it does make its way to the secondary? And Postgres is extensible enough to do that. We've actually done it in the past with something called Citus columnar, or much longer ago, CStore FTW. The problem is that, again, nothing about Postgres is optimized for analytics. So the buffer manager is all these kind of tiny 8 kilobyte pages with a bunch of locking around it, and it's not thread safe. So you cannot really build a very fast parallel query engine on a buffer manager that's not thread safe. So another option would be, should we put the data in object storage? I mean, that's what analytics databases tend to do nowadays. And that actually can work well because then primary and secondary can both just talk to object storage. To make it faster, we could also put maybe a cache in front of that, cache the files locally. Now, as it turns out, there's a table format which is very, very suitable for that, called Iceberg. So Iceberg basically has this layer of metadata files which describe which Parquet files are currently part of the table, what's the schema, which rows have been deleted. And then there's this top-level metadata file that's really like the current version of the whole table. And then there's a catalog that points into the metadata file. And the catalog is kind of the arbitrator of transactions. And basically the catalog is a database. And it can just be Postgres. You can use Postgres as an Iceberg catalog. And so if Postgres can be an Iceberg query engine because we can extend it and use DuckDB to query the Parquet files, and it can also be a catalog, that creates a very simple architecture for using Iceberg that can actually also do transactions across many tables, or Postgres tables and Iceberg tables. So we can write extensions that implement Iceberg in Postgres, where the writes generate Parquet files, Alpha file, JSON files per the Iceberg spec. And where if we query the table, we give part of the query to DuckDB to kind of accelerate it. And then we can still replicate, because and then the catalog table will get replicated to a secondary. So the secondary can also do queries. We could use it as a read replica. Maybe the secondary sometimes is a little bit behind. That's okay, because we'll keep all the older Iceberg files around. That's kind of a property of the Iceberg format. And another nice property of the Iceberg format is all the files are immutable, so we can cache them very aggressively. So we built an implementation of this idea called Crunchy Data Warehouse. And it's basically Postgres extended with Iceberg and these data lake tables for querying CSV or JSON or Parquet files in object storage. And by integrating DuckDB as part of the query engine, for many analytical queries, it's going to be 10, sometimes 100 times faster than doing that exact same thing using regular Postgres tables. And what also helps a lot is that we do write-through caching. So if you insert into an Iceberg table, that'll generate a Parquet file. While we're uploading that into object storage, we'll also write it to a local NVMe drive, such that the next query will just be a local query on a local file. And then the Postgres, you can still also have regular Postgres tables, and they'll be stored in, well, usually something like EBS, a network attached disk. Now, we've been writing Postgres extensions for a very long time, and have some fresh new ideas around how to do that properly. But one of the things we moved away from is this sort of big complex extension like Citus, like one thing that you just throw into Postgres. So now we build much more modular extensions that together form a new user experience. So I think we currently have about 12 extensions that kind of make up the whole Iceberg and data lake table implementation. This also gives us flexibility to say, okay, some of these are open source, like PG Parquet. Some of these are proprietary. Some of these are Rust. Some of these are C. So that's a kind of nice benefit of creating extension constellations. And so what these extensions do is, one of the things they add is this notion of a data lake table. Now, so this is for querying CSV files in S3 or at a URL. You can also query Excel files and shape files and other stuff. Now the problem is you don't really want to sort of have to specify what are all the column names and types in the CSV files. But we cannot change the parser in Postgres via extensions. It's the only thing that isn't very extensible in Postgres. We can overload the behavior of existing syntax because we can intercept every command. And at some point we figured out you can actually create a table without columns in Postgres, which seemed particularly useless. So we thought, okay, let's change what that means. And if you create a table without columns, we'll look at the URL. And then we'll use the DuckDB functions to kind of sniff the CSV file, get the column names and the column types. If it's a Parquet file, there might be nested types in there. And so Postgres doesn't really have a generic nested type, generic structs, or generic maps. So we kind of implemented a map type via another extension. And then when you create a table from a Parquet file that has nested types, we'll automatically generate composite types and maps. And that gives you a very natural way of querying that data. And then if you query that table, we'll basically try to, as much as possible, take that query and give it to DuckDB to query the CSV, query the JSON, query the Parquet. Now, that often involves a bunch of rewriting of the query. So if you select from this table, we'll do a select from read CSV. But also some of the functions in Postgres, like datebin, like DuckDB doesn't have a datebin function, but there's a time bucket function which does actually the same thing. So we have to kind of rewrite some of the expressions in the query to kind of match how DuckDB behaves. And then you can also copy it into object storage or from URLs from object storage. And so the way that query planning process works is, so Postgres allows you to intercept the query at different stages. And I kind of think of it as going through the query from the inside out. Or you could also think of it from top to bottom if you were writing more in pipe syntax, but we don't have that in Postgres. And so we first look at the table scans, which also include the projections and the filters. So if we have all these rules to determine, can these functions, can these operators, can these query constructs be delegated into DuckDB? If yes, then, which is often the case, if yes, then we'll generate some SQL, and then we move on to the next stage of the query planning. Oh, can the group by and the averages and the sums, can they also be delegated into DuckDB? Usually yes, so great. We'll expand our SQL, and we'll look at the next stage. Can the order by limit? Yes, it can also go to DuckDB. Can the whole query go to DuckDB? No, we have a Postgres function at the end that DuckDB doesn't know about. So what we can then do is the part that we were able to delegate becomes a custom scan node in the Postgres query plan. So when the executor starts, Postgres has this sort of volcano executor model, but it basically has this tree of nodes. So it asks the first node for a tuple, and it asks its child's node for the tuple. So at some point it will ask this custom scan node, give me a tuple. And what that will do is it will run the query on DuckDB and then give back tuples. And so you actually get this sort of hybrid query plan, which is partly DuckDB, partly Postgres. And the nice thing about that is that any SQL query still works. And also Postgres has a ton of features like views and rules and inheritance and partitioning that all affect kind of the query result, but those also still work. So that was sort of querying external data. So what about writing into the data warehouse with Iceberg? So we needed writes, and the DuckDB Iceberg extension didn't have writes yet. So we implemented Iceberg from scratch in C. It's probably the only Iceberg C implementation. But so you can then create an Iceberg table just by using the regular create table syntax. You can have generated columns, default expressions, all the stuff you usually have in Postgres, just not indexes and foreign keys. And you say using Iceberg. And here, not too much exciting happens. It'll just go and create a JSON file in S3 or your object storage, and it will insert into the catalog. At that point, the catalog has a view which looks exactly like the table name that the JDBC driver of Spark expects. So you can also point Spark at Crunchy Data Warehouse and query that table directly. And then, for example, when you update the Iceberg table, what will happen is we'll run a query on DuckDB that does a read parquet, and then we just give the list of Iceberg files. We kind of do the pruning on our end. So if based on the query filters, we can skip certain files, we'll leave those out. And then we ask DuckDB, can you give me the file name and the row number of every row that matches the filter? And that goes directly into a position delete file. And then the new values of the rows, they go into a new parquet file. Or usually we're generating multiple files. We don't like to have position delete files that span multiple data files, so we make sure we only write one position delete file per data file. And then we have our own metadata to track which one deletes from which. Then we'll write the new Afro files and JSON files and update our catalog, which is just a Postgres table. And so we can do a bunch of these commands in a single transaction, and we can do transactions across multiple tables. We can do sub-transactions, we can do triggers, we can do constraints. Pretty much everything in Postgres still works, in part because we are our own catalog, so we can manage the transaction. And then when you query that table, what will happen is we'll do a read parquet. And then if there's been an update, there are now position delete files. So these are parquet files that specify from this file name, this row number has been deleted. So we can do this anti-join to filter those out. This is roughly the same thing that happens in the DuckDB Iceberg extension. You can also do schema changes, and recently we added automatic compaction. So Postgres has background workers, and our background worker runs every 10 minutes, and it compacts, it takes a bunch of small files and compacts them together, and it also deletes all the files that are no longer used. And because we can have quite easily aborted transactions or aborted sub-transactions, we also track every file we generate, so that if the transaction aborts, we can immediately clean it up. And then also, like we have this backup window. So if a file is like, as you update and replace files, at some point you don't need them anymore because you don't have to time travel. So we, by default, keep files for 10 days after that. So this sits on top of this kind of hybrid storage architecture. Nothing too fancy. So basically, Postgres has its buffer pool. DuckDB has its own buffer pool. There's the Linux buffer cache. But then, yeah, the Iceberg files, they also kind of go through this NVMe drive. Like at least in our managed service, we use instances with an NVMe drive. So that way we can do queries really quickly. And then Postgres uses Elastic Block Store, and the Iceberg files go into S3 or GCS or Azure Blob Store. So, I know Hannes likes benchmarks, so but we generally compare to ourselves because we have the system that has two types of tables. So we're not usually don't compare to other systems. We just say, okay, here's if we do it with a Postgres table, and here's if we do it with an Iceberg table. So for ClickBench, Postgres is really not good at ClickBench. I think this was an 8-core machine. It takes about an hour to run all the ClickBench queries, and then with caching on Parquet, it takes about a minute, so that's quite a bit faster. We've also done TPCH comparing Postgres to Iceberg. On average, I think it was 14 times faster. And DuckDB is a benchmark that involves a lot of joins, and DuckDB is pretty good at that. The scale factor here is pretty small, like 10, because otherwise it just becomes intractable to run TPCH on Postgres. So why would you actually do this? This is like the what we did, but why do we do it? So can you now run analytics on your operational system of record? Well, maybe, but you really shouldn't. And no one really actually wants that, because your application developers and your analysts, they're probably in different teams, different environments, different tools, different data models. The analysts love transforming data. The application developers are not going to be happy about that. So it's best to keep those separate. But what we see quite a bit is that companies end up having a accidental Postgres data warehouse, as we call it, where they got started building their application on Postgres. It grew quickly. They now have a lot of data. They have business questions, and what they know is Postgres, so that became their data warehouse. And especially for kind of on-prem, we see this a lot because there's not so many great data warehouses for on-prem. And so if you can offer a data warehouse that's like 10 times or 100 times faster, that's a very easy kind of migration. What we also see is that it's kind of useful to add these transactional capabilities into an analytics database. For example, you could have one table where you do very fast inserts. You can do tens, hundreds of thousands of inserts on a Postgres server. And you can periodically flush that into an Iceberg table, and that's a transactional operation. You can still use Postgres materialized views. Building the materialized view will be using DuckDB, but then querying it will be using Postgres and indexes. We also see people like just adding archival in their operational database, writing stuff to Iceberg, to Parquet, or importing JSON. And there's, of course, the sort of data model consistency between your operational and analytical databases. You could now have an analytics database that has the exact same semantics and type system as your operational database, which can be quite useful. So basically, it simplifies your stack, because you can compress a lot of functionality into one box. So you could basically go from the modern data stack into the postmodern data stack, which is just Postgres and DuckDB. Probably other tools as well, like DBT, SQL Mesh, but BI dashboards. But still, you can actually do a lot with just these two tools. So one common use case we see, and we do this a lot internally, operations teams tend to like Postgres. They also tend to have a lot of logs. So one thing we can do now is quite easily incrementally process and transactionally process log files. So we could create this lake analytics table, point it to our logs. We can ask it to add this file name column. We can then create an iceberg table, which could have the same schema or could have some different schema. And then we created this extension that's open source, like PG Incremental, where you can create different types of pipelines. It's built on top of PG cron, which is periodically runs a query. So here's the same idea. We periodically run a query, but every time with different parameter values. And we can then walk through a sequence of time, like for every hour we run this query, or for a sequence of files. Like so new file shows up in S3, we run the query with that file as a parameter or a set of files as a parameter. And so then we can do this insert into an iceberg table, select from the logs table with the file name filter. It'll be clever enough to only read those files. Usually we can actually fully delegate the insert select into DuckDB because we sort of write straight to Parquet. So it's generally really fast. And then this is a sort of fire and forget thing. Because what's nice about this is it internally does the bookkeeping of which files it has already processed. So if anything goes wrong, it'll just roll back and it'll not mark those files as processed. And if it goes right, it'll commit and never process those files again. So the writing to iceberg and the sort of bookkeeping are the same transaction. So this is another example where we create an insert queue for iceberg. So I create an iceberg table. I can use a bunch of different Postgres features there, even like constraints. So then I batch load some data, takes a few seconds. And then when I query the table, it'll use cache. So I can query iceberg in 13 milliseconds. But then if I insert, and I think I recorded this on my laptop, single row inserts are really slow, a few seconds. So let's fix that. Let's create a regular Postgres table with the same schema. We set up a periodic job that deletes from the table and inserts into iceberg. And now we can insert in under a millisecond, which is nice. We can do pretty high throughput inserts as well. And the data's already been flushed into iceberg. And it's still very fast because the Parquet files that I generated went into the local drive. And then every 10 minutes, they'll get automatically compacted. So here I have these sort of nice combined capabilities of transactional and analytical database. One more thing. So, we want to have a feature to announce the data council, but then my talk is the last one of the conference. So we already announced it on Tuesday just to be able to talk about it. So many of you probably already saw it. But what I didn't talk about yet is I'm using Postgres as my operational database. And I want to do analytics on the data from Postgres in this analytical database. That would be great. But how do I get my data from A to B? Now, of course, there's many data movement tools available. But if we're going Postgres to Postgres, we could do something that's much more native. So like just last week, we shipped logical replication from Postgres to Iceberg via Crunchy Data Warehouse. So what that means is that you can go into any Postgres server, be it on our managed service or RDS or Google or wherever, run create publication to say, I want to replicate these tables. And then on Data Warehouse, you can say, create a subscription with the connection string, the publication name, and then you can ask it to create iceberg tables. So that'll go and creates the iceberg tables. It'll copy over the data in the background, and then it starts replicating changes, insert, updates, deletes. It'll accumulate sort of small batches in the warehouse server, but kind of in a durable way. and then it'll flush those into Iceberg every 30 seconds. So the lag is usually less than a minute. And then every 10, because this creates quite small files, every 10 minutes, as usual, we do the automatic compaction. And we spend quite a lot of time sort of finding a good balance between how you actually apply changes and flush changes and do compaction, because that's a kind of a tricky combination. But it works pretty well now. So yeah, this is a demo of the logical replication. So let's say I'm connected to my operational database, my prod database, and I want to run some analytical query. But it just takes forever. Okay, so there are a billion rows in this table, so it takes 4 minutes on Postgres. And it probably uses a ton of resources, so this could cause an outage. So let's create a publication and go to my warehouse. And then I create a subscription, specify the connection string. On our managed service, this can just go through a VPC, or we could also do VPC peering. And so now the data is copying in the background, so the video is kind of fast forwarding, because that takes a while to copy a billion rows. But eventually we're done, and then I can run the same analytical query through the same client, but now it's 300 milliseconds. That's a bit idealized because I haven't had any updates yet, so I don't need to do this where not in join. So let's run a bunch of updates. So this is running 2,500 transactions per second. Every transaction is actually 3 updates and an insert, so it's like 10,000 writes per second. And then on the right, you can see it's like querying the Iceberg table. The Iceberg table kind of moves forward in these jumps where a micro batch gets applied. And one thing that's nice is like the apply is also transactional. So if there's foreign keys on the source, we still preserve those on the destination. Like all the tables get updated at the same time. So that's pretty cool. So in summary, Postgres can give you a quite comprehensive data warehouse, lakehouse experience using extensions, and especially DuckDB with right-through caching give that quite competitive performance. I mean, we'll never be faster than DuckDB, but still we run it in the cloud, so it's close to your data. We cache it locally, so we try to get the best out of DuckDB basically. But then it's single node. You have pretty big nodes nowadays. But if you need to scale, it is also an Iceberg catalog. So you can point PyIceberg with the SQL catalog driver or Spark with the JDBC catalog driver just directly at your data warehouse, and it'll see all the Iceberg tables and can query them. If you need a REST API, there's a project called Lakekeeper, which implements the REST API, and it keeps its state in Postgres. So we can actually internally synchronize with Lakekeeper to offer REST API. So I'd say Crunchy Data Warehouse is the first production-ready solution that does this. It's a compelling architecture. There's a few different projects sort of building something similar. PG Analytics, PG DuckDB, PG Mooncake. A few days ago, I saw PG Pro TAM, and I think we'll probably see more. So let's see how it goes. It's definitely a lot of fun to work on, and I think it's a pretty interesting architecture. So thank you very much for your attention, and happy to answer any questions.